Next up, we have the equation of time. We just talked about a few different celestial definitions, and this is another big one. The equation of time basically tells us how fast celestial bodies are moving, especially the sun, and we'll talk about the numbers we use to calculate how fast they're moving. We do that using the time diagram. This is a way where we can plot our position, where Greenwich is, where the celestial body is, in many cases the sun, and then we can find our LHA, our local hour angle. We learned about declination and GHA in our last lesson, so the big one here is LHA, local hour angle. So let's see what it looks like. We always set up our time diagram as a circle, and that dot in the center is the South Pole. So we're looking at the underside of the Earth. We're basically looking at Antarctica. I'll label that PS, South Pole. Next up comes our meridian, capital M. This is our longitude. It's the meridian that we are standing on. And we always put us on the top up here because that makes it easier to orient ourselves as to where Greenwich is. Since we're looking at the South Pole, over here, if we go this way, that's heading east. And then over here, if we go this way, we are heading west. For this example, we say that we're at 130 degrees west longitude, which means that we're 130 degrees west of Greenwich, which means Greenwich is 130 degrees to the east of us. So the next step of the time diagram is to plot Greenwich. Since Greenwich is 130 degrees to the east of us, we go 130 degrees to the east, and that's where Greenwich is, big G. Some time diagrams have you put in the lower meridians as well. Basically, your upper meridian is the one that you are on. The lower meridian is the one on the other side of the world from you. So our lower meridian would look like this, and it's a little m for lower meridian. Our upper meridian, our actual meridian, is a big M. You can do the same for Greenwich. The lower meridian is a lowercase g, and it's on the other side of the world from Greenwich. We also know that as the international date line. In this case, we're not going to use the lower meridians, just so we don't clutter our time diagrams too much. Now that we have our meridian and Greenwich, we can start to fill in the rest. The next step would be to put where the sun is. Really any celestial body, but most of the time we use the sun. Last lesson we learned about GHA, and GHA is the angle from a celestial body to Greenwich. And it's the equivalent to longitude with one big exception. Longitude is east or west, whereas GHA is always measured to the west. So let's say we go into the Nautical Almanac, we figure out what the GHA of the sun is at this exact point in time, and the GHA is 270 degrees. That means that the sun is 270 degrees measured west from Greenwich. So let's take a look up top again. Since we're looking at the South Pole, this way is west. So if we're going west, we're going counterclockwise. And this way is east. If we're measuring east, we're going clockwise. Since GHA is always measured westward, we're going to be going counterclockwise. So we'll measure from Greenwich. We'll go 270 degrees to the west. It's going to look something like this. And that is the position of the sun. It's 270 degrees to the west from Greenwich, because its GHA is 270. Now that we've plotted ourselves and Greenwich and the sun, we can determine our LHA, our local hour angle. Any hour angle is just an angle from a reference point. So GHA, Greenwich hour angle, is an angle from Greenwich. LHA, local hour angle, is the angle from our local meridian to the celestial body. And just like GHA, it's only measured westward. So now that our time diagram is all set up, we see that we have our meridian and the celestial body, so we are looking for this angle right here. The good news is we already know that this angle is 130 degrees and this angle is 270 degrees, and we're going west, so that makes it easier. So we'll take 270 and we'll subtract 130 degrees from it because we're looking for this angle, and we get 140 degrees. So the local hour angle, LHA, of the sun in this case is 140 degrees. And these time diagrams allow us to map that out and make the calculation much simpler. And this is what it looks like when it's nice and neat. If you want some more practice problems, we have quite a few that you can do in class. Just let us know and we can send you them so that we can really master this concept of where we are, where Greenwich is, and where the sun is. So a quick review. The angle from us to Greenwich is longitude. That's lambda. The angle from Greenwich to the celestial body measured westward is GHA. And the angle from our meridian to the celestial body is LHA. Here are some definitions that we just went over in the last few pages. We talked about upper transit, lower transit, and hour angles. One that we'll cover out later is transits. Whenever we talk about transits, it's when a celestial body crosses a meridian. So for instance, when the sun crosses the Greenwich meridian, that's local apparent noon. The sun is the highest it will be in the sky, and it's not directly above you, but it's on your meridian, so it's either bearing due south or due north from you. It's the exact same thing with the moon and the stars. The one we care about the most is meridian transit of the sun, because as you'll find out much later on in Celestial, if we know when the sun will transit our meridian, that single point in time, we can easily find our latitude. Speaking of the sun, let's talk about the difference between apparent solar time and mean solar time. Apparent solar time is what the sun looks like it's doing. We look at the sun in the sky, and that's what it's actually doing. It's the sun that we're looking at. If you've ever used a sundial, like down here, that is apparent solar time. And the big thing to know about apparent solar time is that the sun does not move perfectly at the same speed. It's different because we have an elliptical orbit around the sun and the inclination of our axis, which we talked about in the last lesson because of the seasons. So every solar day, in other words, the time it takes for the sun to transit the meridian at Greenwich from one day to the next is not exactly 24 hours. That solar day is different depending on the time of year. In order to make the math a little easier for CellNav, we use mean solar time much more often. Let's say the sun is on the celestial meridian at Greenwich at 1200. In one day, the sun has to go 360 degrees around the Earth, and it has 24 hours of time to do that. So if we do the math, if we do 360 degrees divided by 24 hours, we get 15 degrees per hour. That's how fast the sun moves in the sky. That's not how fast it moves through the solar system. That's a totally different topic. A lot more physics involved there. But for us, the sun moves 15 degrees per hour in the sky. And that makes the math a whole lot easier when we do things like arc to time. So you have a parent sun, that's the sun in the sky, what it's actually doing, and then you have the mean solar sun, which is the average sun. We just made the math easier, and that's the mean sun is 15 degrees per hour, that sun. The equation of time is the difference between the mean sun and the apparent sun. So mean time versus apparent time. And it only changes slightly day to day. If you have your nautical almanac, you can open up to any page, any of the daily pages, and look in the bottom right-hand corner, and you'll see this. This tells us what the equation of time is, right here. Let's take an in-depth look at this table. Let's see how this is laid out. You have your days over here. So this is the 25th, 26th, and 27th of May. So this is the 25th. And some information that it gives us is this column tells us what time meridian passage of the sun will occur. And these are all at Greenwich, so this is all LMT, local mean time. So this is at each central meridian as well as Greenwich, since the Greenwich meridian is a central meridian. So it's telling us that on the 25th of May, the sun will transit the Greenwich meridian at 11:57, and that's the apparent sun. You're looking at the sun in the sky, and the sun will cross your meridians. It'll be bearing directly 180 or 000, so due south or due north at 11:57 LMT, local mean time. So the mean sun passes Greenwich at 1200, whereas the apparent sun passes Greenwich at 11:57 LMT. If the mean sun, which moves 15 degrees an hour, then that mean sun, that average sun, that fictitious sun, would be on top of the international dateline, 180 degrees, at midnight, and then 12 hours later it should be directly above the Greenwich meridian. So the mean sun should pass the Greenwich meridian at 1200 LMT every single day. However, in this case, the sun actually transits at 11:57. So I want you to pause the video and think about this question. Which sun is ahead of the other? Is the mean sun or is the apparent sun the one that's ahead of the other one? In this case, the apparent sun is ahead of the mean sun because the apparent sun passed the Greenwich meridian at 11:57, and the mean sun, which always passes at 1200, is about 3 minutes behind it. So by comparing the two, we get the equation of time. In this case, it's about 3 minutes. And we get that all from the meridian passage column. If we take a look at these two columns, the equation of time columns, then we can really get specific at that equation of time. This first column tells us what time the apparent sun will cross the international dateline. The 12H, so 12 hours later, it's telling us what time that apparent sun will cross the meridian at Greenwich. So as you saw, the apparent sun would have a meridian passage at 11:57 LMT. And we see here, we break it down even more. So the apparent sun is 3 minutes and 4 seconds ahead of the mean sun. So for this day, the equation of time is 3 hours and 4 minutes, and the apparent sun is ahead of the mean sun. If we draw it on a time diagram, it looks like this. Celestial bars always transit westward. And if this is Greenwich, this is the lower meridian of Greenwich, so that's the international dateline. You can see that the apparent sun is ahead of the mean sun because they're transiting this way to the west. So we got from the table that the apparent sun is 3 minutes and 4 seconds ahead of the mean sun while we're at Greenwich. And then if we look at the international dateline over here, that difference is 3 minutes and 7 seconds. So what that shows here is that the mean sun is actually slowly catching up to the apparent sun. The good news is about this, that the equation of time only varies a few seconds every day. As we saw in the last example for 25 May, the difference from when it passed the international dateline to when it passed Greenwich was only a few seconds. And during the year, the equation of time can go anywhere from about plus 16 to 20 minutes to minus 16 to 20 minutes. And for the Nautical Almanac, if we get the LMT of meridian passage at Greenwich, we can actually use that for all of those central meridians. So these times in here, we can use them for any central meridian. The last step we would need to do to figure out our zone time of meridian passage is to do some arc to time calculations. In this example from 2015, you can see that for mid-February, the apparent sun crosses the Greenwich meridian at 12:14 LMT, so the apparent sun, in this case, is behind the mean sun. And you can tell that because in the Nautical Almanac, it's shaded in gray. Once you get to around June, mid-June, you can see that now these are all synced up. So the mean sun and the apparent sun are the same. And then once we get into early November, then we can see that the apparent sun is really ahead of the mean sun by about 16.5 minutes. So now if you have your Nautical Almanac with you, I want you to open up to today, even though it might be a different year because we use almanacs from the past. Open up to today and see what the equation of time is for today. I want you to ask yourself, is the apparent sun ahead or behind the mean sun, and by how much? So please pause your video and figure that out. Now that we understand the equation of time, we can use the mean sun for all of our celestial calculations. We calculated earlier that the mean sun, that fictitious sun, has to go 360 degrees in 24 hours, so it moves 15 degrees of arc every hour. That'll make the math much easier for us when we do arc to time, which is the next lesson. So we'll keep moving right along.